Assalamualaikum warahmatullahi wabarakatuh. This is my online presentation for my final year project. I'm Nurul Ramli, a final year student in Bachelor of Science Honors Physics. The title for my FYP is Modeling of CO2 Reduction Process in TIO2 Thin Film. I'm supervised by my lecturer, Dr. Shafi'i bin Muhammad. First, let's begin with introduction that consists of background of study, significance of study, problem statement, and objective of the study. Carbon dioxide CO2 is ubiquitous throughout the cosmos. Carbon dioxide represented chemically by the formula CO2 consists of one carbon atom and two double bonds to oxygen atoms. Carbon and oxygen have many uses in everyday life, such as carbon in the form of carbon dioxide is used in the manufacture of many fizzy and carbonated drinks. Oxygen, while oxygen is used in other applications involving metal and requiring high temperature, such as welding torches. Carbon dioxide is widely used in the food industry, oil industry, chemical industry, biological industry, and many more. Global warming principally causes by the release of carbon dioxide. As a result, carbon management system that reduce global temperature and meet partial energy needs are in high demands. Besides, CO2 also released by the burning hydrocarbon fuels such as coal, natural gas, and oil is now the worst climate polluter at the top of the human greenhouse gas list. In this case, we use a photocatalysis for the CO2 reduction process. Among its catalyst candidates are TIO2, ZNO, and many more. For this study, TIO2 became the main focus of the CO2 reduction process. It is because the TI is more efficient than the semiconductor. But because it is expensive, it must use effectively. So, to understand the mechanism of CO2 reduction plays a vital role in efficient use. TIO2 has been the most thoroughly researched catalyst for photocatalytic CO2 reduction. The purpose of this study is to investigate the CO2 reduction process in TIO2 thin films by varying the position of CO2 in structures using a computer method called modeling. The use or development of computer program to source, analyze, comprehend, or manage molecular structure is known as a computer simulation or modeling. Because of its great accuracy and inexpensive cost, this method was chosen. TIO2 photocatalysis have limitations in fundamental characteristics such as reaction mechanism, selectivity of solar products, and unstable photocatalytic CO2 reduction thermodynamics. In order to boost photocatalytic efficiency, different features of the TIO2-based photocatalytic system must be modified. The mechanism of CO2 reduction by different TIO2 structure is misunderstood, and the needs to elucidate the process of CO2 reduction electronic structure for better understanding of the mechanism. This lesson should be clearly in the path of utilizing density functional theory (DFT) simulation to understand the process of CO2 reduction in TIO2 thin film. These are the objectives of this study. First, to elucidate the CO2 reduction mechanism of different phases, and second, to determine the electronic structures of CO2 reduction for efficient process. Let's move to chapter 2. Molecular modeling is the science of numerically representing molecular structures and simulating their behavior using the equation of quantum and classical physics. It is also one of the fastest growing areas of science. Molecular modeling also a set of computational approaches to control, visualize, and modify the structures and reaction of molecules, as well as the properties affected by these 3D structures. There are three phases to crystallize titanium dioxide, primarily existent in three forms, including the broguide phase or rhombic, anatase phase, tetragonal, and rutile phase, tetragonal. This figure shows the structures of these three phases. Among these various phases of the crystal, the greatest steady phase is rutile, while for nanomaterials, the phase of anatase and broguide are usually more stable than the rutile phase because the surface energy of them is less than that of the rutile. Despite much research, the efficiency of converting CO2 into usable hydrocarbon is still too low for practical application. Further progress requires an understanding of the photoreduction processes at the atomic level, which cannot be obtained without a thorough understanding of the interaction between CO2 and TIO2. This requires an understanding of the structures of the exposed surface, their reactivity, and the binding process at the atomic level. Next, let's move to chapter 3, which is methodology. In this chapter, density functional theory (DFT) is the major The spin polarized functional using cascade package was used in this study. DFT have advantages and limitations, which are DFT is a large gain in computational accuracy without the need for increased processing time. It provides excellent scaling of computational costs with system size and allows computations on large and complex systems. This figure shows an apparatus that was used to perform the simulation, which is Material Studio 2017. Carbon dioxide CO2 was first constructed in the Material Studio, interfaced with 3D automatically employing titanium dioxide annotates as an essential building block for pure structure. Some of the most significant structures are constructed by combining pure annotates with various CO2 locations. The structures were then optimized using the geometrical optimization option in the cascade simulation to ensure structural stability. The geometry for this experiment was optimized using functional local density of approximation known as LD. Several parameters of the CO2 reduction molecule were studied to comprehend the CO2 reduction process in TIO2 thin film. The simulation focused on band structure, density of states, dose electron density difference, and population analysis. The density functional spin polarized calculation was used to explore the molecular characteristics of the CO2 reduction process. Both figures show the setting of cascade calculation to study this parameter. Flowchart of the study. First, start and identify the problem, which is for this study. The problem is investigation of CO2 reduction in thin film, and then run the DFT simulation with docked and undocked to observe the electronic structures and mechanism. From there, the result was obtained. Next, we move to the result and discussion. There are two CO2 reduction structure combination between TiO2 anatase surface with CO2, which are anatase TiO2 plus CO2 and anatase TiO2 plus CO2. All the three structures include pure anatase are the structure that has equal axes A equal to B and equal to C, with all axes are perpendicular to each other, which is 90 degrees. These are optimized structures for pure anatase TiO2 plus CO2 before and after optimization. Next, this is optimized structure for anatase TiO2 plus CO2 before and after optimization. All figures show the geometrically optimized structure of pure anatase TiO2, anatase TiO2 plus CO2, and anatase TiO2 plus CO2 molecules. Geometry optimization was conducted to predict the three-dimensional arrangement of atoms in a molecule to find the stable conformation energy in terms of bond angles and bond lengths for three that mentioned above. The number of states that electrons can occupy at a given energy level is known as the density of states. The electronic dispersion relation of the system attributes are connected with the density of states. Dose analysis is divided into two types, dose and partial p-dose. Total density of states, which is the sum of the dose for the s, p, d, and f orbitals are at a particular energy level is referred to as dose analysis. The maximum of the number of potential electronic states per energy in the s, p, d, and f electron orbital are detailed in p-dose analysis. All three figures depict the dose and p-dose of pure anatase TiO2 plus CO2, and anatase TiO2 plus CO2 molecules with the dose represented as a sum line. The Fermi level is defined in the p-dose analysis as an energy level equal to 0. The Fermi level is the maximum energy level that an electron can occupy at absolute zero temperature. It is also vital to understand that the conduction band is on the right side of the Fermi level, whereas the valence band is on the left side. Band structure analysis shows the range of energy levels that electron can occupy. In this work, band structure analysis was used to figure out the probability of the electron occupation transport mechanism and excited state behavior of anatase TiO2 plus CO2 and anatase TiO2 plus CO2 molecules that will compare to pure anatase to learn more about the properties of CO2 reduction. Anatase TiO2 plus CO2 band gap has a smaller band gap than pure anatase, that is 0.097 electron volt smaller than pure anatase, compared with anatase TiO2 plus CO2 which has a band gap that is even larger than pure anatase is 2.652 electron volt. TiO2 plus CO2 has a wider band gap than TiO2 plus CO2. The wider the band gap, the greater the mass of the electron. This means that there is a large forbidden gaps in energy, preventing electrons from valence bands from jumping up into the conduction band and participating in conduction. This study used electronic density mapping to show the electronic occupancy of anatase TiO2 plus CO2 and anatase TiO2 plus CO2 to orbitals in pure anatase. Electronic mapping shows that the red area indicates a high concentration of electrons, while the blue area indicates a low concentration of electrons. The electronic density mapping for anatase TiO2 plus CO2 and anatase TiO2 plus CO2, two molecules are slightly different, as shown in these figures. For TiO2 plus CO2, we can discern a rich electronic structure near the carbon atom. The oxygen atom is moving away from titanium. This means that oxygen is no longer bonding with the ion. The last part for this online presentation final year project is conclusion. As the conclusion, TiO2 plays an important role as photocatalyst for CO2 reduction. According to Dakshinamurti, most investigations on photocatalytic CO2 reduction have concentrated on the use of TiO2 as a photocatalyst in its anatase form. As a result, the CO2 reduction process was effectively examined in this work using the DFT approach. However, in order to fully comprehend the CO2 reduction process in TiO2 thin film, further investigation into this topic will be required in the future. So, that's all for my final year project presentation. Thank you.